If you are ready, I'm ready. Let's begin. So yeah, my name is Richard Torgbor. The topic actually is chemical formula and chemical equations. But it fall under a broader topic in elective chemistry. They call a conservation of matter and chemical stoichiometry. It is under this topic that will look at how to uh, give the correct names of formulae, how to write the correct formulae of names. You know, I'm talking about IUPAC name of compounds and so on and so forth. We'll look at mole concept, what they call the mole concept, how to calculate mole concentration and all of those things. All of those will be looked at under this topic. Uh, so lesson overview. We, you know, I will be, like I said, I will be interrupting people. I need to be admitting people into the class. So as and when people come, I'll admit them. We'll look at chemical formula and chemical equations. Look at chemical formula and chemical equations. Under this, we'll look at, those of you who are joining us now, please, you are welcome. We've gone through a brief orientation. The class has begun. You have your notes and a pen and everything you need by your side. We'll look at the definition of valency. We'll look at definition of atomicity. We'll look at the definition of radicals and examples of radicals. We'll look at the explanation of oxidation number. We'll explain what oxidation number is. These are the things we'll look at for today. And lastly, we'll learn how to calculate oxidation number of atoms in compounds. These are the things we'll look at in this particular session. Hopefully within the next 45 minutes to 1 hour, we should be done. We've spent quite a bit of time already. So what are the learning objectives? People, by the end of this lesson, students will be able to, you should be able to, one, define the terms valency, atomicity, and radical that are associated with chemical formula. I said from the beginning, the topic is about how to write the name of a compound. So if I give you a compound like NaCl, how do you know the name is sodium chloride? Okay, that's what we want to learn about. That's the first part. Or I give you a compound, a name of a compound like sodium triazocarbonate 4 in words. How will you be able to write the formula, say Na2CO3 for that compound? That's what this first aspect of this topic is about. So to be able to do that, you need to know what valency is, you need to know what atomicity is, you need to know what radicals are. Then we'll define valency, or we'll determine the valency of some elements. After we've defined valency, we should be able to determine the valency of some elements. If I ask you what is the valency of sodium, what is it? What's the valency of potassium? What is it? You should be able to tell me. Then you determine the atomicity of molecules and compounds. I give you a molecule like ammonia, NH3. What is the atomicity? What is the atomicity itself? What does it mean? We'll explain all of these things by the end of this lesson. Then by the end of the lesson, you should be able to give at least 5 examples of radicals with their appropriate formula. You should be able to define oxidation number. What is oxidation number? You should be able to define and explain it. And then lastly, you should be able to calculate the oxidation number of atoms in molecules and compounds. Now, what is valency? Hello, I'm asking you a question. What is valency? Answer, Vigno. I see you are raising your hand from there. I taught you how to raise your hand on the screen. So please practice that. I need you to do that rather than physically raising your hand. Answer, Vigno. I'm waiting for you to raise your hand on the screen, not physically raise your hand there. Okay, I guess you probably joined the meeting late, so but you go on, unmute yourself and tell us what valency is.
Valency is a combining power of an element.
Excellent. So you can mute yourself again so that your background noise doesn't disrupt. That's good. That's what you're taught from JHS. So from JHS, you were told that it is the combining power of an atom of an element. That's right. It can also be defined as the number of electrons gained or lost by an atom to achieve a stable or noble gas state. So for secondary school, this is what we add on to it. JHS is a combining power of an atom or of an element. That's right. Now, if you take an element, you see all the elements we have, all of them, all the 112 elements, all of them want to achieve stability. By stability, I mean they want to behave like the noble gases, where they have a maximum of 2 electrons in the valence shell to achieve what we call the doublet rule for elements like hydrogen, lithium, beryllium, boron. Okay, or they have a maximum of 8 in the valence shell to achieve what we call the octet rule for elements like sodium, potassium, and the rest. So all the other extra electrons in their valence shell, like sodium has only 1 electron in the valence shell. Sodium would like to lose that electron to become stable. Aluminium has 3. The atomic number for aluminium is 13. You know that because aluminium is a 13th element in the periodic table. So that's extra 3 electrons. The JHS configuration, you've been writing 2, 8, 3. For instance, for aluminium, 2, 8, 3. That 3 electrons in the valence shell of aluminium makes aluminium unstable. So aluminium will want to get rid of those electrons so that it can be stable. It then behave like the noble gases. That number of electrons, in this case 3, that aluminium will lose, will give out, is the valency of aluminium. So the valency is defined as the number of electrons gained or lost by an atom. In this case, for aluminium, it is lost, given out. Now, if you take an element like nitrogen, the atomic number for nitrogen is 7. So the configuration is 2, 5. So nitrogen has 5 electrons in the valence shell. Nitrogen needs only 3 electrons to add to that 5 in the valence shell to become 8, so that the valence shell is stable, has 8. Now, nitrogen will not be willing to give out all the 5 electrons it has in the valence shell. No, there's something we call ionization energy. It will not permit that. Rather, nitrogen will accept just 3. You see, it will be easy to accept 3 to add to 5 to become 8 than to give out the entire 5. So nitrogen will accept 3 electrons to become 8. Now that 3 or those 3 electrons that nitrogen accepts is the valency of nitrogen. So again, the valency of nitrogen is also 3. The valency of aluminum is 3 because aluminum can give out 3 electrons. The valency of nitrogen is also 3 because it can accept 3 electrons, not give out 3 electrons. Nitrogen cannot give out 3. It actually has 5 in the valency, but it can't give out all the 5. So it will accept 3 to become stable. The only difference, hello, listen to me, the difference between valency and what we call charge, you see, valency is derived from the charge. The charge has a sign. It's either positive or negative. But valency is the absolute value without charge. So the charge for aluminium is +3 because aluminium will give out 3 electrons. When you give out electrons, you become positively charged and we call you a cation. So the charge for aluminium is +3, but the valency for aluminium is 3 because that's the number of electrons it can give out. The charge for nitrogen is -3. If you accept electrons, you become negatively charged and we call you anion. You are called anion. We did this thing before you guys left for the house. Cation and anion. Cations are positively charged atoms. Anions are negatively charged atoms. So the charge for nitrogen is -3. 3 because it can accept 3 electrons. Minus because it is accepting, not losing. Once you accept, you are minus. But the valency for nitrogen is also 3. So valency for aluminum, 3. Valency for nitrogen, 3. But the charge for aluminum is +3. And the valency and the charge for nitrogen is -3. That's the difference between charge and valency. Once you get the charge, the absolute value without the charge gives you the valency. The valency for sodium is 1. It is 1 because sodium is the 11th element, configuration 281. Okay, 281. So sodium has 1 electron in the valence shell. Sodium will give out that one electron easily. You'll give it out. So the valency is 1 because it's giving out 1 electron. And so the charge will be +1. Now, at the end of this lesson, please hold on for me briefly. Hello, people. I'm sorry. Like I said, today being the first day, parents are, some of your friends are struggling, joining us. So I'll be picking calls to explain some few things to them. That's why I'm sorry. But let's go on. That's about balancing. So I was saying that at the end of the day, every one of you will give me the valency of an element. You choose an element of your own, or I mention an element, and I can see all of your names there. So I'll just mention your name, and then you unmute yourself. Maybe we should do that right now before I continue to the next slide. So I'll give you an element, and then you will tell me, once I mention your name, I can see all of your name. Once I mention your name, I'll give you the element, you unmute yourself, you tell me the valency and the charge of that element for all of us to hear, the valency and the charge. And trust me, I'm staying within the first 20 elements. First person, answer Vigno. Your element is fluorine. So think through it based on what we've said, what will be the charge and what will be the valency of fluorine.
The valency of the fluorine.
Answer, please, and unmute yourself. I think I muted you, sorry. Unmute yourself and come again.
The valency of the fluorine. The valency of the fluorine will be, I guess it will be 1.
Good. And the charge will be what?
The charge will be 12.
The charge will be
12.
no. A charge cannot be as high as that much. Charges are normally between 1 and 3 for the first 20 elements, but the other elements that have variable oxidation state though. What's the atomic number of fluorine?
Okay, thanks.
Answer, what's the atomic number of fluorine?
Atomic number. Atomic number will be 2. Yeah.
Are you sure? The atomic number of fluorine is not 2.
Yeah.
Fluorine is the 9th element. Okay, on the periodic table, fluorine is the 9th element. Hydrogen, helium, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. So if you count that, you see that the fluorine is the 9th element. So the JHS configuration, or the configuration we've been using from JHS, 2, the first shell takes 2, and the second shell takes 7. So you see that the second shell, which then becomes a valence shell, has 7 electrons. It needs just 1. It needs just 1 electron to add to that 7 to become 8. The rule is they all want to become 8. They want to have 8 in the valence shell. So fluorine will accept 1 electron, just 1, to add to that 7 to become 8. That makes the valency 1, like you rightly said. And because it is accepting, okay, it is accepting, you negate it. So the charge becomes -1, -1. Okay, let's go on. I'll come back to the rest. Answer, you can unmute yourself. You can mute yourself, sorry.
Okay.
So look at atomicity. It refers to the number of atoms or amount of atoms in 1 mole or molecule of a substance. The number of each atom is placed as a right subscript of the symbol of the element in the molecule. So anytime you see a compound or a molecule, the number of atoms in it is the atomicity of that molecule or compound. Just a minute, please. Hello, people, I'm back. So that's atomicity. If you take a molecule like hydrogen gas, you can see two atoms. You see two written at the bottom there. So the atomicity of hydrogen is 2. That's all. If you take O3, O3 is what we call ozone gas. There are 3 atoms of oxygen. So the atomicity is 3. That's all. If you take P4, of course, phosphorus, there are 4 atoms. So the atomicity is 4. If you take CO2, you can see there is 1 atom of carbon and there are 2 atoms of oxygen. So the atomicity is 3. If you take ammonium, NH4, there's ammonium actually has a plus at the top, ammonium. The atomicity is 4 because you can see 1 atom of nitrogen and then 4 atoms of hydrogen. If you sum them up, you have a total of okay. So that's about atomicity. So if you take a molecule, let me give you an example that is not here. A molecule like or a compound, not a molecule, a compound like NaCl, sodium chloride. There's only 1 atom of sodium and 1 atom of chlorine. That's Cl. So the atomicity is 2, just 2. Meaning in that compound, there are just 2 atoms or elements in that compound. That's about atomicity. If you take one like H2CO3, all of you write down that compound, H2CO3. H, then subscript 2, and then CO3. It's not here. You can't see it on the screen. In that compound that I've given you, you see there are 2 atoms of hydrogen. There is 1 atom of carbon and then there are 3 atoms of oxygen. Please, it's not on the slides. It's not on the slide. That example is not on the slide. So 2 for hydrogen plus 1 for carbon plus 3 for oxygen. That gives you a total of 6. So in that compound I've given you H2CO3, the atomicity is 6 because in all you have 6 atoms in there. So that's how you determine atomicity. We are still continuing with the definition of terms. Radicals. Rosemont Malman. Please unmute yourself. What do you remember about radicals? What are radicals? Any idea? Rosemont, if you need to talk, good. You've done that. You've unmuted yourself. So go ahead and talk. Everybody. All right. Cindy, any idea? Radicals. Done. Done, I think your mic, Donette, you need to unmute yourself. You've not unmuted yourself, so we can't hear you. Okay, let me unmute everybody right now. And then, yeah. So, Done, go on. Done, we can hear you. Just go on. Done, it looks like you have a problem with your device. You're unmuted, but I can't hear you. Okay, so try and Prince, Novo Prince, any idea what are radicals? Okay, there is a, that's good. There's somebody by name Trial Account. Trial Account. I see your hand up. I guess you joined the meeting late. So I'll need you to change that name, Trial Account, to your real name and put your class beside it. But go on, please. I can hear you.
Okay, so please, radical is a molecule that contains 1 ampere electron.
Okay, you've tried. That's fine. Prince Novo, can you hear me?
Please, yes.
Go on, please.
it it contains unpaired electrons.
I see. I see you people have just been eating, sleeping, and enjoying at home. You've not been doing any reading. Okay, valency. All right, let's go on. Let me mute all of you. Let's go on. So as you can see on your screen now, JHS, you were told they are a group of atoms which stay together as a charged unit. Oh, did I say valency or radicals? I'm actually referring to radicals. I was actually referring to radicals. I guess I was asking you for valency. Sorry, I was referring to radicals. Yeah, so radicals are a group of atoms that stay together as charged units. They are also called polyatomic ions. So you see a group of atoms, with a common charge. In the next table or in the next slide, I'm going to show you examples of radicals and their common names. Every radical has its common name and its IUPAC name. Now, this class is about getting the IUPAC name of those compounds, those radicals, and also compounds. So these are some radicals, and their common name. On the left-hand side, you see radicals, and then at the right-hand side, you see their common names. See OH minus, called hydroxide. H3O plus, called hydrozonium. Cn minus, cyanide. NH4 plus, ammonium. NO3 minus, nitrates. NO2 minus, nitrite. I want you to take note of the difference between the two, the nitrates and then the nitrite. You have NO3 minus, that's nitrate. NO2 minus, nitrites. It's important. These things are absolutely important to be able to give the correct names of compounds. Now, the last two at the bottom, you see similar things. You see SO4 2 minus, sulfate. Then you see SO3 2 minus, sulfite. So the difference is A and I. Just in nitrate and nitrite, you see the same difference, just between, just the words, the alphabet A and I, making the difference. NO3 minus nitrate, NO2 minus nitrite, SO4 2 minus sulfate, SO3 2 minus sulfite. All of you, no exception, all of you must know these radicals by heart. You must find a way of committing the names of these radicals to memory, because you need them to be able to write the correct formula of compounds and give the correct names of compounds. So when I say ammonium, when there's the word ammonium in the name of a compound, you know ammonium is NH4 plus. You should be able to come to your mind quickly. That's the only way by which you'll be able to give the correct name of the compound. When I give a name of a compound and you see the word sulfate in the name, you should be able to know that sulfate is SO4 2 minus. You have the third one from the bottom, C2H3O2 minus, is called acetate. Okay, so let's go on. You have another one here, and this is the last slide for examples of radicals. I've given you quite a lot, and there are many, many radicals out there that, please, if I mute you, don't unmute yourself. James Salom, please, there's some noise at your background. mute you, you unmute yourself. Please stop that. Like I said, if you have any question, just raise up your hand. Go to the participant. What I showed you, raise up your hand. I'll see it, and then I'll give you the chance to ask the question. You don't have to unmute yourself if you have any question. You need to know these radicals and match them against their names. ClO3 minus chloride. Okay. Anybody has any question? James Salom, if you can hear me, please stop unmuting your device when I mute you. If you have any question, raise up your hand. All right, no questions. So I'm going on. Please, like I said, it's important. If you want to know, writing of names or formula, or writing of formula of names, you need to know this very well. When I say carbonate, what's the formula for carbonate? CO3 2 minus. You should be able to tell me CO3 2 minus. You see, all of them have charges. All of them have charges, either a plus or a minus. That's why they are called radicals. Let me go to the previous one for you to see. All of them have charges. That's why they are called radicals. They are a group of atoms that are together. They are a group of atoms that are together and they have a common charge. So they are called radicals. Now, the last thing I want us to look at is oxidation number. This is the last thing. We'll look at oxidation number and how to calculate oxidation number, and that's where the lesson for today will end. Oxidation number is also known as oxidation state. Oxidation number is the same as oxidation state. So when you go to an examination, they ask you to define oxidation state. It is the same as being asked to define oxidation number. It is defined as the real, or what we call the hypothetical charge. Hypothetical means like imaginary or an assumed charge, a charge that is not real, that an atom carries in its pure state or in its compound form based on given rules. And those rules are what we call IUPAC rules. So I think in the year 1938 or so, a group of chemists, a group of scientists met in France. That's why we have SI unit and so on and so forth. Please, somebody is destroying my screen. Who is doing that? Stop, please. So they came up with names of compounds that H2O should be called water. You see, CO2 should be called carbon dioxide. Based on certain rules. Those rules are what we call IUPAC rules. And we'll look at them as we go along. But this is the definition for oxidation number. Hello, people, can you hear me? Rosemond, can you hear me?
Yes.
Okay, all right. So let's go on. Now, what are some of these rules that govern the way oxidation numbers are assigned? So what you see on your slide in red, rules in assigning oxidation number to atoms. You need to know these rules because it guides the way we give oxidation number to atoms. It's absolutely important. You need to know the rules, but you don't need to memorize them. No, there's no need. Nobody will ask you to state the rules, that are used in assigning oxidation number to atoms in any examination. No, but you need to be familiar. You need to familiarize yourself with the rules because you need the rules to be able to calculate the correct oxidation number of atoms in compounds. Now, rule number 1. The oxidation number of a pure element in its atomic or molecular form is 0. Example, the species O2, O3, P4, S8, and Al, aluminium, all have an oxidation number of 0. So if a molecule or a compound is in its pure state, the pure state is what we call the uncombined state. Uncombined state meaning, just that same element, not combined with any other element, okay, in a compound. You have just one element. The oxidation number it has is 0. If there's no charge on it, it's 0. So you see O2, that's oxygen gas. This oxidation number is 0. So if I ask you what is the oxidation number of the element oxygen in the molecule O2, you tell me it's 0. It's 0. That's the rule. You need to know that any molecule that is given, the oxidation number of an element in that molecule, once it's a pure molecule, okay, or pure element. A pure element, I mean, just made up of that element, that atom alone, the oxidation number is 0. The second one, the oxidation number of a simple ion is equal to the charge on the ion. Example, the oxidation number of sodium in Na plus ion is +1, and the oxidation number of chloride of chlorine in the Cl minus ion is -1. So if I give you a simple ion, what's a simple ion? A simple ion is an ion made up of just one element. So F minus, Cl minus, Na plus, O2 minus, K plus, Mg2 plus, Al3 plus, calcium 2 plus. Those are all simple ions. They are simple because it's just one element that has a charge. You know what an ion is? An ion is a charged particle, a charged atom. It's an ion or a charged species. So the word ion there should not confuse you. Anything that has a charge is an ion. If you have a group of atoms staying together and they have the same charge, that's what we call radical. Okay, if it's just one element with a charge, it's called a simple ion, like Na plus. It's a simple ion. The charge they have is the same as their oxidation number. Take note of that. Then the third one, III. The oxidation number of hydrogen is always +1, except in metal hydride. Example, CaH2Al H3NaH, where it is -1. Anywhere you see hydrogen in any compound at all, its charge or its oxidation number is +1. Unless the compound in which you see the hydrogen is what we call a metal hydride. Metal hydride will mean hydrogen combining with a metal. Hydrogen combining with a metal. And there's a topic, metal and non-metals. We'll look at that later. But metals are those elements that give out electrons. They form positive ions. So sodium, potassium, lithium, beryllium, aluminium. Those elements, if you take the periodic table, those elements that are to the left side, the left-hand side, those are the metals. The ones to the right-hand side are the non-metals. Normally, I know I was teaching the class one day, I asked students to give me examples of metals. Yeah, they're giving me, box iron, they're giving me nail, they were giving me, in fact, somebody even mentioned our basketball rink, as an example of a metal. People were giving me cutlass, and so on and so forth as metals, because some of the things they mention can actually attract magnets. So they say they are metals. Now, metals are actually elements. So what are metals? Metals are elements. You need to start like that. They are elements. Okay, elements that give out electrons to form positive ions are the ones we call the metals. So anytime any of those elements combine with hydrogen, then the oxidation number of hydrogen ceases to be +1. But it becomes -1 in those instances. The oxidation number of oxygen is always -2. That's the next one, except in compounds we call peroxides. Compounds we call peroxides like H2O2. That's what we call hydrogen peroxide. Na2O2. That's what we call sodium peroxide, and so on and so forth. Compounds we call, for instance, the hydrogen peroxide. If you go to, they sell it mostly in the markets, at the park stations. It's always in some small brown bottle, or brown bottle. They use it as a mouthwash. They say if your mouth is smelling, you use it to rinse your mouth. That's hydrogen peroxide. You fetch small, add water, dilute it, and then use it to rinse your mouth for a number of times and pour it. That's hydrogen peroxide. When you have oxygen in those compounds, it's all of them H2O2, Na2O2. We have others like K2O2, that's potassium peroxide. Oxygen is -1 in that. I'll show you how to calculate the oxidation number pretty soon. But apart from that, in all other compounds, oxygen is -2. That's its oxidation number, which is the same. In fact, there's a fine difference. There's a fine line between oxidation number and the charge of an atom. In many instances, oxidation number is the same as the charge. In many instances, it's the same as the charge. But there's a fine difference between them. Then also in compounds we call superoxides. Examples: H2O2, HO2, KO2, NaO2. Those are compounds we call superoxides. So the first one, HO2, the element there is hydrogen, so we call it hydrogen superoxide. You see the difference between that one and the first one? Hydrogen peroxide. That one is H2O2. This is hydrogen superoxide, HO2. The oxidation number in this compound, hydrogen superoxide, is -1/2, not -1, not -2. It's -1/2. So anytime you are giving any compound like this, you see they take the same format: HO2, KO2, NaO2, LiO2, in that order. And you ask what is the oxidation number of oxygen in that compound, it's always -1/2. And you can calculate it. I will show you how to calculate it and arrive at that -1. Now, the total of the oscillation numbers of all atoms in a neutral entity is 0. That's the next rule. Rule number 2, actually. The total of the oscillation numbers of all atoms in a neutral entity is 0. A neutral entity here means, species or a compound. So if I give you a compound like NaCl, sodium chloride, what is the oxidation, or what is the charge on that compound? Is 0. Once you don't see anything at the top, it is 0. Now the last one, the total of the oxidation numbers of all atoms in an ion of more than one atom is equal to the charge carried by the ion. So for radicals like OH minus, CO3 2 minus, the charge of, or the sum of the oxidation number of all the atoms in that radical should be equal to the charge that is on the radical. Okay. So these are the rules. Now the next thing is to use this third rule. The third rule is very important. We use it in calculating the oxidation number of atoms in molecules. But I will pause here. I imagine a number of you are exhausted, the struggle and all of that joining. I will pause here and take some questions if you have any. And the next time we'll meet, we'll actually make use of this final rule in actually calculating the oxidation number of atoms. That's important. I don't want to load you at this point with that one. So we'll pause here. That's the last thing as part of the objectives that we've not been able to cover. So folks, I'm done. If you have any question, please just raise up your hand. I'll see it. I'll call your name. Then you unmute yourself and then you ask the question. Did you answer? I see your hand up. Please unmute yourself and ask your question.
Sir, please, you said you explain how we get a -half.
Yes, I will explain that. I will show you how come the oxidation number of oxygen in compounds we call peroxides is -half. Not only that, but also in compounds we call superoxides, why it is -half, and in compounds we call peroxides, why it is -1. But that's for the next lesson. Like I said, that's about calculation, how those answers or those charges are arrived at, the -half and the -1, how they are arrived at. I would show you in our next class.
Thank you.
Welcome. Please put down your hand. Answer. Okay, I'm going to unmute all of you briefly, and all of you, I'm going to unmute you. And let me find out. Hello, everybody. Do you understand what we've done this morning? Anybody has any challenge, any questions? Okay, I have muted all of you again because there's so much noise at the background. So I've muted all of you. If you have any question, just raise up your hand and ask. Okay, I don't see any hand up. So I have, questions for you, 1 or 2 questions, and then we'll end this session. So I'll ask the question, I'll mention your name, and then you unmute yourself. And Done, if Yati, I can see you the way you've done your face. You don't like you don't like me to ask you questions. Seke Alien, I see you too. You're welcome. You joined quite late, but I can see you. So I'll ask the question, and then you think through it, unmute yourself, and answer the question. A couple of questions, 1 or 2. Then we'll bring this session to an end, so that you can go take breakfast and prepare for the next class. Okay, we start somewhere around 11:30 or so, 11. So, what is the valency? The valency of the element sulfur. The element is sulfur. You see, I explained, if you're asked to state the valency of an element, all you need to do is to write the electronic configuration of the element, the GHS1. But you first of all need to know the atomic number of the element. What's the position of the element on the periodic table? Once you do that, you write the electronic configuration, say 2, 8, so and so. If the element has, less than 4 electrons in the valence shell, okay, the number of electrons it has in the valence shell, if it is less than 4, that's its valency, because that's the number of electrons it will give out. So if it has 1, the valency is 1. If it has 2, the valency is 2. If it has 3, the valency is 3. If it has more than 4 in the valence shell, like 5, it has 5, it has 6, it has 7, it will accept a certain number to become 8. And the number it will accept for it to become 8 is then the valency of the element. So if the element has 5 in the valence shell, it will accept 3 to become 8. So the valency is 3. If the element has 6 in the valence shell, it will accept 2 to become 8. So the valency is 2. If the element has 7 in the valence shell, it will accept 1 to become 8. So the valency is 1. All right, so let me ask the question again. What's the valency of the element sulfur? Eze, Arinze. Eze, Arinze, if you can hear me, just unmute yourself and attempt the question. We can hear you. Go on, please. Come again.
6.
No, please. You see, you are close. It has 6 electrons in the valence shell, but the valency is not 6. Because 6 is more than 4, how many electrons must it accept to become 8? It will accept 2 to become 8. And so the valency is 2, not 6. Okay. What's the valency of the element oxygen? Florence, Yaira. Florence, Yaira, if you can hear me, please unmute yourself and attempt the question. Okay, all right. Prince Novo, what's the valency of oxygen?
Zero.
Come again.
0. 0.
No, the valency of oxygen is not 0. The valency of oxygen is 2. Mr. Joseph Jamesi, I see your hand up.
Sir. Sir.
Yes, please go on.
Sir, please, I only raised my hand only to answer the question of the valency of oxygen to be 2, not raising my hand to ask a question, sorry.
Okay. I get you. Yes, the valency of oxygen is 2.
Okay.
The valency of oxygen is 2. Nero, I wasn't talking, Prince, I wasn't talking about the charge or the oxidation state. If I ask for the oxidation state, just oxygen, you will tell me it's 0. But the valency is 2. Since the valency is 2, the charge is -2. What it means is oxygen can accept 2 electrons. Oxygen and sulfur, okay, they are in the same group of the periodic table and they behave the same way. They accept 2 electrons each to become stable. What's the valency of boron? Rosemont, Malman. Okay, what's the valency of boron? Anybody raise up your hand? Boron is the 5th element in the periodic table. What will its valency be? Rosemont, you can, Rosemont, go on.
1.
No, please. Seraphine Vomadi, please go on. Unmute yourself and go on.
The valency of boron is 3.
Excellent. Excellent. The valency is 3. Boron is the 5th element in a periodic table. So if you write the configuration will be 2, 3. You see, so it has 3 electrons in the valence shell. That 3, it will give it out. And we define valency as the number of electrons given out or accepted before the element becomes stable. So the valency of boron, I hope you understand. It's important you take note of these things. Then, good. Then I said you should study this table to know these radicals by heart. People, if you want to know how to give the correct formula of compounds, the correct names of compounds, these things, they should be at your fingertips. You are the ones that will have to learn these things. You are the ones that will have to commit these things to memory, not me. I can only talk about them and direct you, but you have to do the work. If you are sleeping at dawn, somebody comes to wake you up. Hey, donate. What is the formula for ammonium? You should be able to wake up and say, oh, ammonium is NH4 plus without thinking, meaning the things are at your fingertips. That's what I want it to be. That's how I want it to be. You should know them by heart. These ones and the ones on the next page, these ones, a lot. And I said there are a lot. There are a lot more than even what I've put over here. But these are the most common ones you will encounter, you will meet in your everyday study of chemistry and everyday naming of compounds. After Desmond, can you hear me?
Yes, sir.
Oh, good. That's good. All right, so let's go on. We did all of these things the last time. And this is where we ended with this, small example that we solved in the class. Assign oxidation numbers to the atoms underlying the following compounds or ions. This is where we ended. I remember we solved all of them. and I said I gave you an assignment on Google Classroom. Some of you did it. Some of you are yet to do it. So after today's class, I'll give you another assignment. Okay, I'll give you plenty of assignment that you work over the weekend. And I think I'll meet you on Monday. So I would like to receive them on Sunday. Anytime I give you assignment, I will attach a deadline to it. Please, all of you should do the work and submit the assignment on time. So that when we meet on Monday, I can point out some of your mistakes to you. It's important you do that. Today, I'm talking about a new thing. We are moving on. Savannah to 4. Your hand is up.
Say,
Yes, madam.
say. Then what of we those who were not, around the beginning of the class?
Okay, that's a very good question. What I would do is that I will get some time and then go over some of the things we did before you join the class. Yeah, I think I can do that. So that's what I can say to that for now.
Okay.
Yeah. So yeah, but it's good you join now. So just pay attention and let's go on. Okay. In fact, some of the things we did earlier on may even come up that I may need to talk about them briefly as we go along. So IUPAC. Now we are actually, going to the real naming of the compounds, and this body of scientists, they basically came out with a set of rules that govern the way compounds should be named. And that body of chemists is what we call IUPAC. And IUPAC, as you can see on your screen, is just an abbreviation for International Union of Pure and Applied Chemistry. So the I is international, the U is union, the P is pure, the A is not the, or the end is not for the A, no. The A is applied, and then the C is chemistry. So the end and then the off between union and pure are just there to join the words. It sounds like a proper sentence. You can't say International Union of Pure. You can't say International Union Pure Applied Chemistry. No, it doesn't make sense. International Union Pure Applied Chemistry. You see, it doesn't make sense. So the off serving as some conjunctions, linking the word so that there is some clarity to the whole phrase or clause or whatever. I guess it's a clause, right? Okay, you are the ones reading the English. So anytime you are asked in an examination, what is IUPAC? Just say it is an abbreviation. The word IUPAC is an abbreviation for International Union of Pure and Applied Chemistry. That's all. It's a body of chemists that met and design rules to follow in naming compounds. So that leads us to what we call IUPAC nomenclature. IUPAC nomenclature. The word nomenclature just means naming. Nomenclature. I remember when I went to secondary school, I was very, very, very young, very, very small. So a senior saw me. In those days, seniors are always giant and tall, and it's not like the seniors we have these days. Seniors we have these days are, are very small seniors. Those days, seniors, when you see them, you know that this is a senior. You are scared even of them. Call me and say, "Hey, young man, come here." He said, "What is your nomenclature?" I say, "Yehovah." What kind of word is this? I haven't heard before. Then he asked me what program I'm coming to read, at the secondary school, Sogasco, Sogakova Secondary School. Then I said I was coming to read science. And he said, "Look at you." Apparently, the senior was a visual art student, visual art. They are even more, giant, masculine than you can imagine. So look at you, call yourself the science students. I'm even a visual art student. Come on, your nomenclature, you don't know. I felt so bad. Then in the course of our studies, I got to know that the word nomenclature just means naming. Naming. So the senior was just asking for my name. See, I just asked me, hey, young man, what is your name? You want to show me? You want to bully me with words? What is your nomenclature? So the word nomenclature just means naming. Now, it's a system of naming chemical substances, or a system of naming chemical substances is called chemical nomenclature. It's chemical naming. One of such systems is the IUPAC nomenclature. So IUPAC nomenclature is just one of those systems that is used in naming. In fact, it is the most common one. It is what we actually study in secondary school. All the compounds we name: sodium chloride, carbon dioxide, water, sodium carbonate, and the rest. All of them are named not based on any other system, but based on the IUPAC system of naming compounds. The IUPAC nomenclature is also called the IUPAC system, IUPAC systematic naming. And I said the word nomenclature means naming. So what is IUPAC nomenclature? If you take your past questions, you see this question: define IUPAC nomenclature. What is IUPAC nomenclature? IUPAC nomenclature, and that's the last sentence there, is therefore defined as a system of naming compounds according to the rules of IUPAC. It's a system of naming compounds according to the rules of IUPAC. Please, it's important that all of you know this definition. I've explained to you what IUPAC is. IUPAC is International Union of Pure and Applied Chemistry. It's a body of chemists that came up with rules as to how to name compounds. Then nomenclature means naming. So if you put the two of them together, IUPAC nomenclature, it is a system of naming compounds using the rules of IUPAC or based on the rules of IUPAC. Now, this system of naming compounds, this IUPAC system of naming compounds has some advantages. Just like in biology, you talk of classification. You see, classification, compounds needed to be named so that it helps, scientists in communication and so on and so forth. But aside that, the systematic naming of compounds gives information about the oxidation state of the compound. In fact, if you add the oxidation state of all the elements within a compound, then you will get the oxidation number of the compound, which invariably is the same as the charge of the compound. It also gives information about the number of atoms combining to form the compound. Okay, once a name is given to you, a name like sodium chloride, you can actually tell how many elements are combining to form that compound if you understand IUPAC system of naming compounds correctly. If I give a name like sodium triosocarbonate 4, if you understand IUPAC system of naming compounds correctly, you can actually tell the number of atoms that are combining to form that compound. So that's one thing the IUPAC system of nomenclature reveals to us or gives us. Now, in the IUPAC system of naming compounds, there are some names we call common names of compounds or the trivial names of compounds. What are they? Now, these names are old and traditional names. They are not necessarily based on any rules. For example, the common name for the compound H2SO4 is sulfuric acid. I'm sure you've heard that before. Names like that are what we call the common name or the trivial name, the common names. Sulfuric acid, H2SO4. H2CO3. That one is not on the slide. Carbonic acid. You've heard that before, I'm sure. Carbonic acid. phosphoric acid, Then H2O, water. You are familiar with that one. NH3, ammonia. Now, some of these common names of compounds have been accepted and integrated into the system, and they have become known as the IUPAC names of these compounds. So the IUPAC name for water, for H2O is water. H2O is water. Even though the water is a common name initially, it's now been accepted as the IUPAC name, so that nobody goes about naming H2O as a hydrogen oxide. No, that's wrong. There's nothing like that. Hydrogen, that's wrong. So that nobody goes about naming NH3, you see, ammonia. Nobody goes about attempting to give the IUPAC name of NH3 as nitrogen trihydride or anything. No, that's wrong. Simply ammonia. Ammonia is a common name, but it's been accepted as the IUPAC name for NH3. The last one is methane, CH4. Nobody goes about naming methane as a carbon tetrahydro or whatever. No, there's nothing like that. It's wrong. It's just methane. These are some of these common names have been accepted and are used as the IUPAC name of these compounds. And the compounds that have these common names as the IUPAC names are very, very few. They are very, very few. Almost all compounds have their common names. They have their common names, and then they have their IUPAC names, which are different from their common names. Few of them, like water, ammonia, their common names are the same as their IUPAC names. Hey, I hope you are all listening, paying attention. Donate. Your face is not on the slide. Your eyes are not on the slide. You are looking somewhere else. I am seeing almost everybody's face. So if your face is not here, I will mention your name. I will name and shame so that you pay attention. Remain focused on your slides. Okay, so what I'm going to do, in fact, we have variety. What we're going to do now is I'm going to take you through all the species you can think about and how to name them. Whether it is a simple cation, whether it is a simple anion, whether it is oxo anions, whether it is oxo acids, salts, bases, double salt, and so on and so forth. How are they named? That's what we're going to do in the next few slides. And I'll need you to pay special attention. If you follow me, carefully, by the time we are done, you should be able to give the IUPAC name for every or any compound that you are giving any examination at all. That's why I'm starting from a very simple one. Simple cations. As the word suggests, simple cations. First of all, what is a cation? Peggy, Janji, at 3. What's a cation?
Cations are positively charged atoms.
Yes, that's correct. You are right. Cations are positively charged atoms. That's correct. So when I add the word simple to it, simple cations, what then does it mean? If I ask what's a simple cation? What is it? Perfect, a dye. Yes. Yes.
There are simple positive charge atoms.
But you're using the word simple again. You're very smart, oh. You're telling me they are simple, positively charged atoms. Cations are positively charged atoms. So simple cations should be simple positively charged atoms. Wow. I like that smartness, but it is the word simple that I want you to explain in addition to the cation. Okay. All right. So when we say simple cations, they are cations that are made up of just one element. Okay, you see a cation with just one element. So say sodium plus, potassium plus, Ca2 plus, Mg2 plus, Li plus, lithium plus. Simple. You see the radicals, I'm sending you back to the radical table. These radicals, okay, so yeah, this one, the hydrozonium ion and ammonium can be referred to as complex cation because they are made up of more than one element. You have more than one element forming the cation. So the radicals are actually complex cations. Okay, the anions will also be complex anions. But if you have a cation where there is only one element, just one element forming a charge, then that cation is a simple cation. So that's the definition of a simple cation. Simple cations are cations made up of only one element. Now, how do we name them? There are some rules. Rule number one, the name of the element is written first, plus the word ion. So if I give you Na plus to name, the rule says that give the name of the element first. Give the name of the element first, then you add the word ion to it. Look at the bottom of the second point. Li plus. Li is lithium. So you just write the word lithium because Li stands for lithium. Then you leave space and you add the word ion to it. Ion because it is charged. It has a charge. So if you don't add the word ion to it, you are wrong. You see, Li will be named as lithium. The element lithium, Li. If you have Li plus, it is not lithium. It is lithium ion. So you have to add the word ion to it. That's the first rule, that the name of the element is written first, plus the word ion. You write the name of the element, then you leave space, then you add the word ion to it. That's all. The ion, I-O-N. Okay. I know some of you say GHS, they told you that word is ion. Ion. Well, I call it ion. I believe it is called ion. But whatever it is, whether it is ion, ion, Ewing, whatever it is, the spelling is the most important thing. Just make sure you get the spelling right. It is I-O-N, ion. Look at the second one. Al3 plus. Which element is Al? I see Al over there. Which element is Al? It's aluminium. So I write aluminium, I leave space, and I add the word ion. That's all. That's the name. That's the name of Al3 plus, aluminium ion. Aluminium ion. Now, what does this mean? These first few examples, what does it tell you? It tells you that you need to know the symbols of the elements by heart, to people. For those of you who are not doing science, you need to, okay, well, let me say for integrated science. I'm actually teaching integrated science chemistry. You need to know at least the first 20 elements by heart. Now, in addition to the first 20 elements, you need to know some of the selected elements and their symbols, some of the common elements I think I will have the chance to teach you, to talk to you briefly about the periodic table. Maybe if you are doing metals and non-metals, and then I will talk, a bit about that. You need to know other elements in addition to the first 20 elements. Their symbols is enough. You don't need to know their atomic numbers. You need to know, for instance, that Zn is zinc. You need to know that that's a common element, even though it's not within the first 20 elements. You need to know. You need to know Cu is copper, or copper is Cu. You need to know that. You need to know that Hg is mercury. You need to know that. What is the symbol? Let me give you a teaser. What is the symbol, the chemical symbol for the element tin? Tin, the element tin. Justin Jamesi.
Sn.
Sn. What is the symbol
Yes, sir.
for the element manganese? Rosemond, Malman.
Amen.
Excellent. Mn. You need to know them. Okay? You need to know them. What is the symbol for the element Pb? Perfect adai. Pb.
Lead.
Come again.
Say said.
Perfect, you're not listening to me.
So I couldn't hear well.
Lead.
Okay, I
Who
was
is
asking
that?
you. Hey, is that perfect? Who is that? Perfect. I was asking what's the symbol for Pb for the element. Oh, sorry.
Salad.
No
Okay.
idea.
I was asking you what the symbol for lead is, which is Pb. That's fine. All right, let's go on. So I'm saying that you need to know them by heart. Okay. Hey, those of you who, please be disciplined, okay? If you are not the one I've called to answer a question, please keep quiet and let's listen to whoever I've called. All right, look at the second rule on your slides. Hey, all of you, do you have the slide, the slide with the heading IUPAC naming of compounds and species, A, simple cations? Do you have this slide on your screens?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Excellent, excellent. Now look at the second rule, rule number
Yes,
two.
sir.
Excellent. Look at the second rule. If the element is an element that shows variable oxidation state, comma, or variable oxidation number. I told you before, oxidation state is the same as oxidation number. Its oxidation number is written in brackets in capital Roman numerals immediately after its name, before the word ion is added. Let me take it again. If the element is an element that shows variable oxidation state, that shows, variable means not fixed, changes. Okay. If the element is an element that, or whose oxidation number changes, whose oxidation number is not fixed, then that element's particular oxidation number at that particular time in that particular compound must be written in brackets in capital Roman numerals immediately after the name of the element before you add the word ion. Now, what does this mean? There are a number of elements, well, not a lot though, but there are some elements that show variable oxidation state. What that means is that, let me give you an example. The element ion. Ion alone have two charges, so two oxidation states. In some compounds, ion is +2. It has a charge of +2 or oxidation state of +2. In other compounds, it has oxidation state or a charge of +3. Copper is another example. In some compounds, copper has a charge or oxidation state or oxidation number of +1. In other compounds, this oxidation state changes to +2. So these elements, copper, iron, and a number of them that have variable oxidation states, whose oxidation numbers are not stable or are not fixed. It keeps changing from compound to compound. These elements, if you are giving their names, their IUPAC names, as simple cations, when you write the name of the element, you need to indicate the particular oxidation number that it has in brackets, in capital Roman numerals. You leave space before you add the word ion. Look at this example, Fe3 plus. Fe3 plus. That's what I'm talking about. Look at the name, ion 3 ion. Ion 3 ion. You see the name of the element is ion, I-R-O-N. So ion is written. Then what is its oxidation state? The oxidation state is +3. One of the earliest rule we look at is that for single elements that are charged, the charge they carry is their oxidation number. I think rule number 2 or so. You can go back to the rules in assigning oxidation number is there. So ion is +3 in this case. So the oxidation number is 3. Ion is +3 in this case. So the oxidation number is 3. That oxidation number is written in brackets in Roman numerals. As you can see, in Roman numerals 3. Then space before the word ion is added. Another example, Cu2 plus. Copper is another element that shows variable oxidation state. So copper, then the oxidation number in this case is +2. So the 2 is written in brackets in Roman numerals. Then space before the word ion. I know some of you are thinking already and you have questions to ask. Say, but how would we know which element shows variable oxidation state and which one doesn't? So that the ones that do, we put the oxidation number in brackets. Yes. I will soon give you a table of those elements that show variable oxidation state. Your job is to look at those elements and get familiarized with them. Familiarize yourself with those elements so that anytime, anywhere you see those elements, you know that, this is part of those group of elements that show variable oxidation state. So the way you name them must be different. The way you approach their naming must be different. The last example here on this slide is Zn2 plus. It's just zinc ion, Zn2 plus. It's just zinc ion. Why is it not zinc 2 ion? Because zinc is not an element that shows variable oxidation state. Zinc is just like aluminum and lithium. That's how come its oxidation number 2 is not put in brackets in capital Roman numerals. In fact, the elements that show variable oxidation state, a lot of them are elements we call transition metals. If you take the periodic table, they are a group of elements that are located at the center of the periodic table, between the metals that are to the left and then the non-metals that are to the right. There are a group of elements at the center there. We call them transition elements or transition metals. Many of the elements that I'll be giving to you as elements that show variable oxidation states are elements that belong to that category of elements we call the transition metals. In fact, that's one of their properties. One of the properties of transition metals is that they have variable oxidation state. Zinc is not actually a transition metal. Even though zinc falls within that bracket of element, it isn't a transition metal, and there are specific reasons why it isn't a transition metal. So I see some books, they've been writing zinc 2 ion, zinc 2 carbonate, zinc 2 chloride. Please, those things are wrong. Don't mind them. Zinc doesn't show variable oxidation state. So it's just zinc. The compound should just be named zinc chloride, zinc iodide, or whatever, not zinc 2. No, that's wrong. I've also seen in some books where you see the second one, aluminum, where some people are just so confused with these rules. So they say aluminum 3, and I'm sure you've come across some of those before. Aluminum 3 triazocarbonate 4, aluminum 3 chloride. That's also wrong. That's wrong, completely wrong. Aluminium is not an element that shows variable oxidation state. In fact, aluminium has a fixed oxidation state of +3. Aluminium is always +3. It doesn't change to +1 or +2 anywhere. It is always +3. So there is no need putting the +3 in brackets in capital Roman numerals. So those books that have indicated that, they are all wrong. It's just aluminum chloride, not aluminum 3 chloride. But we'll get there. So, folks, this is about the simple cations. These are few examples how they are named. You should be able to name every other cation. They give you a cation like Ca2+, Ca2+. Write it down. Ca2+. What is a Ca? Well, I need to know Ca is calcium. So I write calcium. Then, because it is +2, it is an ion. So I add the word ion to it. That's all. That's the name of Ca2+. It is called calcium ion. Calcium is not an element that shows variable oxidation state. No, it doesn't show that. It has a fixed oxidation state. So there's no need putting into bracket 2. No, it's just calcium ion. And like I said, I'll show you a table very soon that has those elements that show variable oxidation states. So that once you see them, you know how to approach their naming. But that's all for simple cations. Let's look at simple anions, the direct opposite of cations. What is okay, Ellie, go on.
An anions are negative charge ions.
Okay, anions are negatively charged atoms. Okay, anions are negatively charged. Anions are negatively charged atoms, or an anion is a negatively charged atom. Anions are negatively charged atoms, or an anion, meaning you are defining the singular one. An anion is a negatively charged atom. That's correct. So again, when I add the word, simple to it, then you know that Sylvester Stanham, you have something to say? Okay. So when I add the word simple to it, it means it's a single element, an anion made up of just one element, like Cl minus, like S2 minus. I'm not talking about being made up of a single charge, no, like charge is -1, no. No, that's not where the focus is. The charge can be 2, the charge can be 3, the charge can be anything. The focus is that the element bearing the charge, or the species bearing the charge, is just one element, like Cl minus, like O2 minus. How are they named? The suffix IDE replaces the last 2 or 3 letters in the name of the anion, and the word ion is added. The person doing that should stop. The person annotating should stop. The suffix IDE replaces the last 2 or 3 letters in the name of the anion, and the word ion is added. suffix, prefix. You remember those two words, right? Prefix are letters, alphabets, okay, or group of alphabets that are added before a word. They come before a word. So prefix. You fix them prior to the word. You fix them prior to the word, prefix. The direct opposite is suffix. They come after the word, so they are at the end of the word. In naming anions, the suffix IDE, that one, those three letters, IDE, replaces the last two or three letters in the name of the anion. Then you add the word ion to it. That's all. Example. Look at the first example. Cl minus. They asked you to name that in an examination. That's very simple. Cl is chlorine. But IDE replaces the INE in chlorine. That's the last three letters in chlorine. INE. Replaced by IDE. So that chlorine becomes chloride. Then you leave space and you add the word ion. If you don't add the word ion, you are wrong. You just say chloride. No, it's an ion. Chloride ion. In fact, some people also say chlorine ion. That's also wrong. That's not the correct name. If you say chlorine ion, even though it makes sense, but that's not the IUPAC name. Junior Bansa, your hand is up. Please unmute yourself and ask your question.
Sir, please, can the ion come before the chloride, or
so that the name is like ion chloride?
I'm
No.
asking whether the ion can come before the chloride.
No, please. That would be wrong.
Yes. Okay.
All right. So let's go on. O2 minus become oxide ion. In fact, there are some of the elements. It is not the last two or three. It is actually the last four. If you look at oxygen, oxygen is OXYGEN. OXYGEN. In the case of oxygen, it is the last four letters. That's YGEN. YGEN. That gets replaced with IDE. So that oxygen becomes oxide ion. Oxide ion. That's how it is named. The same thing applies to nitrogen. If you look at the spelling of nitrogen, nitrogen is NITROGEN. So it is the last four. Ogen, like ogen or ogen. OGEN. The last four letters there. That gets replaced with IDE. So it becomes nitrite. Nitrite. Now look at this carefully. You know, this is different from nitrates and nitrites. Those are radicals. Nitrate is NO3 minus. Nitrite is NO2 minus. Those are radicals. This is just nitrogen as an anion, and it's called nitrite. Nitrite ion. So please take note of these differences. We have nitrates, we have nitrites, then we have nitrite. So that will be all for simple anions. That will be all for simple anions. Then the third category of compounds you need to know is binary compounds. And after binary compounds, we'll end the class. This is where we'll stop. But let's go through the binary compounds to the end, and then I'll give you a homework on the Google platform. What are binary compounds? Anybody has any idea? Rosemont, Marman, your hand is up. That's good.
Sir.
Please go on.
These are compounds containing atoms of two different elements only.
Excellent. Excellent. That's good. Please mute yourself. They are compounds that have atoms of two different elements. Two different elements only. You will see only two elements in them. It doesn't matter the number of atoms they have. There can be 20 atoms. The element can be made up of 5 atoms, but there must be only 2 elements, not more than 2, not 1. Not more than 2, just 2. We call them binary compounds. These are compounds containing atoms of two different elements only. Example, CuO, NaCl, HCl, SO2, etc. The atoms of one of these elements are more electronegative, attract electrons more towards themselves than the atoms of the other element or of the other. So these are examples of binary compounds. You need to know what binary compounds are. In integrated science, you can be asked in an examination, define binary compounds and give 2 examples. Just tell the examiner, oh, binary compounds, they are compounds that contain atoms of 2 different elements. That's all. And give the examples, plenty examples. Look at the examples I've given, and I will allow you people 1 minute. Everybody will give me 1 example of a binary compound. Now, before we begin, you look at the last example I've given you, SO2. You see, SO2 contains 3 atoms. So it contains 3 atoms. 1 atom of sulfur, 2 atoms of oxygen. That makes it 3 atoms. So atomicity, its atomicity is 3. But it has only 2 elements. The elements are sulfur and oxygen. That's the difference between these things. Binary compounds are compounds that you can say binary compounds are compounds that contain 2 different elements only. Contains 2 elements only. That's all. The emphasis is not on atoms. So if you go and define binary compounds as compounds containing 2 atoms only, you are wrong. Then in that case, you are saying that even O2, oxygen gas, is a binary compound. Because oxygen gas contains 2 atoms, but of the same element, oxygen. You are wrong. There has to be 2 atoms, but of different elements. And the elements, it has to be 2 different elements. 2 different elements. It doesn't matter the number of atoms. The number of atoms can be 5, can be 10, whatever it is. But the elements must not be more than 2. It must not be 1. It must just be 2 to be called a binary compound. That's all. Now, Ike Dionu Emmanuel, you give me a compound that you can think of that is binary.
Say aluminum chloride.
Aluminum chloride is excellent. It's a binary compound. Please mute yourself. There's so much noise at you people, your background. So, hey, anytime you unmute yourself to talk, it's crazy. Gen 2 said them. Gen 2 said them. If you can hear me, unmute yourself and give us 1 example of a binary compound.
Okay.
You can give me the formula, not okay. Sodium chloride. I think you people are looking on my screen and giving my examples. Let me go back. Yeah. Dennis Rowe Agble. Okay, Dennis Rowe, can you hear me? Okay, L, say Ram.
Say NH3.
Come again.
NH3.
NH3, ammonia. That's a binary compound. You're right. It has one nitrogen. It has nitrogen and hydrogen. That's fine. But L, is that your name? Is your name Learl? What does it mean? What is that the name? Come again.
Yes, sir.
So which one
yes,
is
sir. Yes.
which one is the surname? Is the L the surname or Sayram?
No, I did not add the surname. I'm about to add it.
Okay, so all of you need to add your surnames. I said that earlier on. Okay. After Desmond, one example of a binary compound. Say H2O. H2O. That's very simple. Good. Dodoja, Stephanie, MFA. One example.
So,
Stephanie, come again. I don't know whether it's my end here, but Stephanie, it looks like your network is not stable at all. I'll get back to you. Pearl, Jom, Alate.
NH4.
NH4, okay. But with a NH4 with a plus over there. All right, but I hear you. It has two elements. That's okay. Peggy, Janji.
CaCl2.
CaCl2. Excellent. Excellent. Rosemont, Malman.
Say.
Yes.
H2O.
H2O. Somebody give that already, but that's fine. Pogo, Rejoice. One example.
H2S.
Oh, that's excellent. That's terrific. H2S. That's good. The last example, Nolin, Bena. Give us the last example, then I'll move on. We'll move on.
Lead oxide.
That's excellent. Lead oxide. That's excellent. I hear you. So that's good. You need to know them. These are things they also ask sometimes at objective. See, which of the following compounds is not a binary compound? Then you see A, NaCl, B, CaCl2, C, H2O. All those three are binary compounds. Then you see the D may be Na2CO3, see, Na2CO3. That's sodium carbonate. Na2CO3. It has three elements: sodium, carbon, and oxygen. So that will be the one that is not a binary compound. It then becomes the right answer to choose. Okay, let's go on. Now, how do you name binary compounds? You see, the binary compounds are actually like bringing together simple cations, a simple cation, and then a simple anion. So you see, the rules will be a combination of these two. The first rule is that the name the first element first. That is the more electropositive element. So when they give you the compound, it will have two elements. You have two elements. I didn't say two atoms. I say you have two elements. The element that comes first is what is named. You give that name first. That element is an element you refer to as the more electropositive element. Okay, I didn't say the element that forms a cation. That element, well, okay, let me explain that. What we mean by the more electropositive element is the element that has a better tendency, a higher propensity to become positively charged. It doesn't mean that the element, is an element that can form a cation, because if you take the compound SO2, the first element over there is sulfur. Sulfur doesn't form positive ions, it doesn't. But in this compound SO2, sulfur is the one that has a higher tendency to become positively charged. Sulfur has a better ability to become positively charged than oxygen has. In elective chemistry, I would have been telling you that what we call ionization energy of sulfur is lower than the ionization energy of oxygen. So it will be easy for sulfur to form positive ions than it will be for oxygen too. So sulfur is named first in that example. The rule is that you name the first element first. Now, in naming that first element, if that first element is an element that shows variable oxidation state, then you will need to indicate the oxidation number of that element in capital Roman numerals, in bracket or in parentheses, just after the name of the element, or immediately after the name of the element. So you see examples like you see carbon 4, copper 2, iron 3, iron 2, etc. These are all elements that show variable oxidation states. So just when they come, you need to indicate the oxidation number. But say, how will we know the oxidation number of the element? That's what some of you are thinking right now. Say, how will we know the oxidation number of the element? Well, that's why we learned how to calculate the oxidation number of the elements or of elements in a compound. And when we take specific examples, I will throw more light on that so that those who didn't join the class from the beginning can have some idea as to how to calculate the oxidation number of elements in atoms. Then the third and the last rule is that the last 2 or 3 letters in the name of the second element, and that second element is an element that is the more electronegative element. What does that mean? It means that element has a better ability, it has a higher propensity, tendency to form negative charges, to form negative ion than the first element has. Again, here, if we're doing elective chemistry, I'll be telling you that element will have a higher electron affinity than the first element. That element will have more love to accept electrons than the first element, will. So that element has a better ability to form negative charges. Those are the elements we refer to as electronegative element. The more electronegative element is replaced. So the last 2 or 3 letters in that element is replaced by the suffix IDE. You see, this is the same as what we did when we were looking at simple anions. Oh, some people are just going on and off. Perfectadie went off and had to admit her again. That's sad. I think the internet, at some people's end, is not stable at all. So chlorine becomes chloride, oxygen becomes oxide, fluorine becomes fluoride, carbon becomes carbide. Carbon becomes carbide. Carbon also has, if carbon is combined with some other elements, carbon can have a better ability to form negative charges than the element it is combined with, especially with metals. So like CaC2, CaC2, calcium combining with carbon. In that case, carbon is the element that has a higher ability to become negatively charged. carbon is the more electronegative element. So in that case, carbon becomes carbide. Carbide. Take note of that, it's important. The table below shows examples of elements that show variable oxidation state and their oxidation numbers. This is the table I promised that I will give to you. So you have 3-column table. Column 1 is symbol, column 2 is name of the element, or just name over there, and column 3 is oxidation state. As for column 3, don't worry about that. I don't want anybody to go and memorize this, it's not necessary. What I need you to do is to familiarize yourself with this element. Get to know these elements by heart, so that once you see these elements in a compound, you know that this is an element that shows variable oxidation state. This is an element whose oxidation number is not fixed, it changes. And so that will inform you how to name the compound. Gold is one of them. Thallium is another one. Copper, as for copper, I mentioned it already earlier. Mercury, iron, carbon, sulfur, chlorine, bromine, iodine. Now I'll come to them. These elements are elements that form anions. They are not transition metals. Sulfur is also part, and the rest. Why are they also elements that have variable oxidation state? Yes, they do. When they combine with oxygen, let me talk to this guy. Ikedionu Emmanuel, I think you need to, Ikedionu Emmanuel, I just admitted you, if you can hear me, you need to let your parents work on your network, okay? Maybe change your location, because you keep going and coming on and off, please. That's not helpful, because you get to miss some of the parts. So I am begging you, Ikedionu Emmanuel, I just admitted you, or I guess I'm talking into his sound is not even connected. Sound is not even connected. Perfect, Adai, you can also hear me. You also went off along the line, and I had to admit you again. I think it's about the individual networks, so you need to work on that, because I know there are people. Eugene Dekuma, you have something to say? Okay, so I was making the point that there are some people who have been. Yes, Eugene.
So I have nothing. So
then why are you unmuting your sound?
it was a mistake.
Don't be making mistakes, people. I was making the point that there's been some people who have been hooked onto the class from the very beginning when I admitted them, and they have been consistent. There's not been any interruption for over 1 hour now, getting to 1.5 hours, or even getting to 1.5 hours already. Yeah, just about some 20 minutes, and meaning their networks have been pretty stable. So I know all of us are in different locations, but even in the location where you are, you can locate another location within that location where the network is a bit better than where probably you are right now. So that, okay, you understand, there's some consistency. Yeah, for those of you who are missing out of the small ones, we are we are always recording these things. Very soon we'll start uploading them. We'll give you the links so you can watch on YouTube. We'll send the links to you. Say, the ICT Master has converted all of these videos very nicely. We don't want you to download them because the sizes are big. You use a lot of data in downloading them, but once it is a link, you can just go there and watch and listen. It's better. You spend few data. So we'll send the links to you. We'll also send you the these slides, these notes. We'll send them to you in the Google Classroom. Please don't give it out to your friends, those who haven't paid. If you give them the link and you give them the note and all of those, you are cheating yourself. You have paid, so they haven't paid. So the person is your friend, to tell the person, well, go and pay. At times we need to make friends. At times we need to unmake friends. Okay, so let's go on. I need you to take, a critical look at these elements. Pay special attention to these elements. This is not all. This is the last batch. Nitrogen is also one. Chromium is another. Nickel is another. Cobalt is one. Tin is one. Manganese is one. Lead is one. Titanium is another. You need to know these elements by heart. When I say know them, I mean know them that they are elements that show variable oxidation states. That's all. Don't worry yourself about knowing whether the charge is +2 or +3, whether it is +1, +2, +3, or +4. No, don't worry about that. That's the third column. Don't worry about that at all, because I've taught you how to calculate the oxidation number. So whatever it is, you'll be able to, deduce it yourself, derive it. I need this table, this list of elements, okay, to be by your bedside. Write them in your notebook. Let them be by your bedside. First thing in the morning, you wake up, you just glance through. See, I believe in this theory of familiarity, familiarizing yourself with the materials. The more and more you look at these materials, these elements, trust me, you are not memorizing, but you are just familiarizing yourself with them. The more you look at them, I am telling you, the more they get recorded in your mind. This theory works a lot. It works a lot. It works magic. So that anytime you see this element in any compound, this is an element said shows variable oxidation state. So I have to calculate its oxidation number to know what particular oxidation state or number it has in this particular compound they've given me to name. That's how these things work. So write them down nicely in your notebook, put them by your bedside. First thing in the morning, you wake up, you read it, you go through, look at these elements. Let this become what you use for your morning devotion. You look at the Bible, you read the Bible for morning devotion. Many of you don't even read the Bible. Then you go through this element to small. You look at this element to small. The last thing. Sylvester, Sanam.
Sir.
I'm listening.
Sir, please, can you scroll up to the previous one? I want to take a screenshot so that I can copy the notes later.
Okay, all right, that's fine. Well, like I said, I will give you, you can take the screenshot, you can write. But just know that I will give you this note. Okay? I'll give you this note. But it's good you write. Because when I give the note to you, it can only be on your phone. Or you can print as well. But it's good you write. Can I move on?
Yes, sir.
The last thing, examples. The last thing we'll look at. After all that we'll look at now. Please, just a minute. All right. Sorry for that interruption. Please, let's go on. We were looking at work examples. Give the IUPAC
Sir.
name of the yes.
Sir, please, somebody is annotating the screen.
Who is that? Why are you people like this?
Somebody just wrote L on the screen.
Okay, thank God I didn't even see it. Okay, I've seen the person. Hey, who at all is doing this? All right, let's. I think sometimes it is a bit of ignorance. I'm telling you, the person probably doesn't even know that he or she is doing that. Just see some icons, you are clicking on them, you don't even know what they are, and then just doing so many things. You need to know that whatever you are doing at your end, appears at other people's end. Okay. Give the IUPAC name of the following compounds: NaCl, FeO, Fe2O3, CaCl2, MgC2. So I'll give the name of the first two, and then the last three, I'll mention people's name, students' name to give us the answer. The teacher always does the simple ones and leaves the difficult ones for the students. You see the first two, they are very, very simple. I will do that. And the last three, you will do that because you are the students. The first one, sodium chloride. That's all. It's as simple as that. The first element is sodium. So sodium. You leave space. The second element is chlorine. Chlorine becomes chloride. That's part of the rules. So sodium chloride, that's all. Now, you see, in writing the second element to have started with a capital letter. And it's another thing that is gradually, missing in chemistry books. They write sodium and then the chloride, they start with small c. It's actually wrong. It's wrong. It has to start with a capital C. That's the right thing. There is space. You leave space. As for the space, yes, they leave it. But the chloride, the second element, most of the time, they start with a small c. That's wrong. Now, look at the second one. FeO. I see Fe, that's ion. I know that it is an element that shows variable oxidation states. So I have to calculate its oxidation number. I have to find out what its oxidation number is. I just wanted you to know that there's actually no space between this. Yeah. So I calculate the oxidation number of ion. I have 2. How did I get the 2? Those of you who are not with us on Monday, you let X be the oxidation number of Fe. That's what I want. Why do I want it? Because I know it's an element that shows variable oxidation state. So I have to find out what is its oxidation number in this particular compound. So X for the ion, that's what I want. I don't know it. Plus that of oxygen. Oxygen is always -2. The charge or the oxidation state of oxygen is always -2 in all its compounds, except in 2 groups of compounds we call peroxides, where it is -1, and another group of compounds we call superoxides, where it is -1/2. Otherwise, it is always -2. So X plus -2 is for oxygen, should be equal to 0. That's the charge on the compound. The compound has no charge, so 0. So if you solve for X over the X, you send the 2 to the other side, it becomes X is equal to 0 plus 2. X will be equal to +2, +2. It tells me that the oxidation number of ion in that compound is +2. And since it is an element that shows variable oxidation state, once I bring this name ion, then I have to bring the oxidation number in brackets in capital Roman numerals 2. So you can see that. Then I leave space. And then the name of the more electronegative element, the name of the second element comes oxygen. Bearing in mind that the suffix IDE must mistake must replace the last 2 or 3 letters in its name so that oxygen becomes oxide. So the name is iron 2 oxide. That's the name of that compound, iron 2 oxide. Iron 2 oxide. All right. That's what the teacher has done. What about the third one, the students, the fourth one, and the fifth one? You have 1 minute to work through the second one, the third one, the fourth, and then the fifth one. Where I start calling names. Oh, people are raising their hands already. That's good. Joseph, Kumuntum.
Sir,
Go on, sir.
iron 3 oxide.
Iron 3 oxide is correct for 3 points. Iron 3 oxide is a name for the third one, as you can see. Iron 3 oxide. Excellent work. Calculate the oxidation number of iron over there. You get 3. You get +3. The next one, I see Bansa. No, Bansa, you hold on. Bansa, hold on. Peggy, Janji. Peggy, you are on. Go, please.
Calcium chloride.
Calcium chloride is excellent for 3 points. Calcium chloride is correct. Now, I am happy that Peggy didn't say calcium 2 chloride. Peggy didn't say that. Calcium chloride, that's all. Why? Because calcium is not an element that shows variable oxidation state. So take note of that. Bansa, Maunyo.
Sir, magnesium carbide.
Magnesium carbide is the name of the last one. Magnesium carbide. That's excellent. Magnesium carbide. There's nothing like magnesium 2 carbide. No. Because magnesium is not an element that shows variable oxidation state. It's just magnesium carbide. It's just magnesium carbide. So the fourth one, like you rightly said, calcium chloride. The fifth one, magnesium carbide. Now, oh, okay. I was actually supposed to solve all of this and give you some to try. I didn't even know. So give the IUPAC names of the following compounds. So those of you who are raising your hands, more for you. IZNCl2, CuO, LiCl, MgO, Al2O3, MgH, CuS. More work for you to try. Donate, Piati, the first one.
Zinc chloride.
Zinc chloride is excellent. Zinc chloride is excellent. Please take note of that. That compound is not zinc 2 chloride, as it is named in some books. The second one, Gloria Sam.
Say.
What's your name?
Gloria Sam.
Gloria Sam.
Yes.
So your surname is Sam, right?
Yes.
Okay. So you give me, let me change that. I think I can rename it. I don't want the Gloria Sam. So let me name it Sam Gloria. Your program is what? What program are you doing?
Say. At 3.
Okay, at 3. All right. I've just named it for you.
Okay.
I've changed the name. Okay. What's the name of the compound? The second. Excellent. Excellent. Copper 2 oxide is correct for 5 points. Copper 2 oxide. Copper 2 oxide. I'm happy you didn't say copper oxide. You didn't say copper oxide. You said copper 2 oxide. Because copper is an element that shows variable oxidation states. So you need to calculate this oxidation number. X for copper minus 2 for oxygen is equal to 0. The charge on the compound. X will be equal to 0 plus 2. X is plus 2. So copper 2 oxide. Good work. The third one, let me Alien Seke.
Yes, sir.
Please go on.
Sir, lithium chloride.
Lithium chloride is as simple as that. Lithium chloride. The fourth one, this should actually be the fourth one. Not the third one again. Then this is supposed to be the fifth, the sixth, the seventh. Good. Let me see who will answer. Sydney McCarthy.
Magnesium oxide.
Magnesium oxide is correct. That's correct. Magnesium oxide is correct. The fifth one. Kenneth. Kenneth Ebrison.
Yeah, please, I'm not done solving it.
The fifth one. But your hand is up.
That's the previous one.
The previous one.
Sir.
Yes. Senam, Sylvester.
Yes, sir. Aluminium trioxide.
Aluminium trioxide is wrong. By the way, what's your surname? Sylvester,
Dogbedo. So I'm not come to add it.
You add it, eh?
Dogbedo. Yes, sir.
Okay. Exe.
Ah.
Exe, Arinze.
Please. Aluminium oxide.
Aluminium oxide. Aluminium oxide is correct.
I didn't make this one. Why isn't this one?
Hey. You people, you need to know, I told you that this app is very sensitive to sound. So if you are done talking, you want to talk to somebody at the background, you need to mute yourself. Why are you even talking to somebody at the background whilst we are in class? Eh? Okay, the sixth one, Vigneault answer.
Sir, magnesium hydride.
Excellent. That's an excellent one. Magnesium hydride. Hydrogen, in this case, is behaving like an anion. Hydrogen is the more electronegative element. So the suffix IDE replaces the OGEN so that hydrogen becomes hydride. The compound is magnesium hydride. And the very last one, Novo Prince, are you still on the platform?
Yes.
All right. What's the name of the last one?
Copper 2 sulfide.
That's incorrect, Prince.
Sir.
Who is talking?
Copper 3 sulfide.
That's incorrect.
Copper
Justin.
4.
Copper 1 sulfide.
Sir, copper 1 sulfide. Copper 1 sulfide.
Copper 1
Copper 1 sulfide.
Copper 1 sulfide is correct. Copper 1 sulfide is the right answer. Okay. So listen, Prince, you said copper 2 sulfide because I guess you are looking at the 2 at the bottom over there for copper. So that's the rule. Don't allow those numbers that are written there to determine the way you name the compound. No. Or to determine the way you name the compound. If the element, you've been able to identify the element as an element that shows variable oxidation state, then what you need to do is to go ahead and calculate the oxidation number. Just calculate it. Because the numbers written at the bottom over there are subscript. Sometimes, no, not sometimes, all the times, are not their oxidation numbers. They are not. So you need to calculate and be sure. Let X be the oxidation number of copper. That's what you want. And there are 2 atoms of copper. So 2X plus what's the oxidation number of sulfur or the charge? Sulfur is -2. Sulfur is a group 6 element. You need 2 electrons to become stable. How do I know that sulfur is -2? Oh, sulfur is the 16th element. So configuration is 2, 8, 6. There are 6 electrons in the valence here. You accept 2 to become stable. So sulfur is -2. How do I know sulfur is the 16th element? Well, then he helped little berry boy count number of flowers needed. Okay, those songs, that's what will help you. You know that sulfur is the 16th element. Configuration is 2, 8, 6. It needs 2 to become stable. You accept 2, so the charge is -2. So 2x minus 2 will give you 0. If you solve for x, x is +1. So copper is actually 1 over there, not 2. The oxidation state is +1, not +2. So that the name of the compound is copper 1 sulfide. Copper 1 sulfide, not copper 2 sulfide. Ladies and gentlemen, that brings me to the end of my lesson today.